So luckily, nobody has even come close to touching on what I'm going to touch on here. So tonight, I'm going to introduce you to the concept of the Sloposphere, which was a term coined by Rich Briggs and Justin Rubenstein at the USGS, and why some of you should maybe be considering the Sloposphere, particularly given the boundaries between tectonic geodesy, geomorphology, and paleoseismology that continue to be blurred. The Sloposphere simply is the shallowest mechanical layer of the Earth, the upper 200 to 100 meters or so, and it's notable as the home of the slop. So slop, most of you are probably fairly familiar with. It's essentially earthquake geology. So measurements from trenches, displaced landforms, surface ruptures, different displacements that can occur in a range of different complex materials and behave in a bunch of different ways. Characteristically, slop is very complex and noisy. It's very contradictory sometimes and sometimes counterintuitive. A very good example of slop is the intense variability that can happen around a surface rupture. Geodetically, we have very excellent evidence for the presence of slop. Most of you will recognize it as data misfits that are caused by unmodeled shallow Earth complexity or non-elastic near-fault deformation, otherwise known as permanent deformation. And in my opinion, one of the very best examples of slop, or the influences of slop, is the shallow slip deficit that several folks have identified. Now, the Sloposphere itself is pretty important to us because it's where we make all our geodetic observations, which means that we observe all crustal and lithospheric processes through the filter of the Sloposphere. Despite this, it's the layer that is one of the most commonly ignored layers by earthquake geodesists, and there's a couple of good reasons for this. First of all, what do we see here? This is the Earth, right? This is our nice, uniform, elastic half space, the SuperBall Earth, or the Okada sphere. This is the simplest way to parameterize a potentially infinitely complex inverse problem, right? So it's a way to introduce the least amount of user bias in the absence of any other information. Moreover, this works a lot in nature. Consider the Sumatran subduction zone, which uplifts and subsides repeatedly over many seismic cycles, but over geological timescales doesn't move. It's essentially deforming purely elastically over many hundreds of thousands to millions of years. Now, I forgot what my, okay. The second reason is that we've only been able to make these observations geodetically recently. I was born in 1986, so one full generation ago, when UNAVCO had 3 GPS sensors, and earthquakes more or less looked like this. A couple of point measurements that were pretty noisy, and the best you could do reasonably was fit them with an elastic model. Now, in the early 1990s, of course, imaging geodesy exploded onto the scene. And for the first time, getting ahead of myself, wasn't I cute? For the first time, we could really start to observe and measure the full spectrum of deformation around an earthquake, from the far field SuperBall Earth elastic deformation to the near-fault slop-dominated near-fault displacements where an earthquake turns into geology. And now, with all kinds of new advancements in imaging geodesy, we're at the point where we can measure slop, and basically we're measuring geology, okay? We're measuring the Earth as it appears with 2 different examples here, one a geological map and one geodetic-based map. Now, the simple question is, this is a lot of can do. I can do a lot of different things here, and the question everybody should ask is, well, so what? What are you going to do with it? Are you going to incrementally make a slip distribution better? You know, that doesn't necessarily advance any science. So I think folks working on things like shallow fault mechanics have found a really interesting pathway. So I'm going to introduce a different one. I want you to consider the geologic timescale and the broad spectrum of techniques that geoscientists have to make observations of processes that span something like 15 orders of magnitude of time, okay? There is a very critical gap in our observational capabilities between the portions of a single seismic cycle that we observe geodetically and seismologically and the integrated multiple seismic cycles that are seen in the paleoseismological record. If we were to ever understand how the processes that we observe today translate into the geological record, and vice versa, how the geological record accurately informs the hazards of tomorrow, we have to understand what happens in this gap. And it's my view that that link is made in the Sloposphere. So I'm going to end with this functional thought experiment and with a charge for my generation and the next generation of geodesists, which is to embrace the Sloposphere, explore the Sloposphere, and really start to interrogate the Sloposphere. Thank you.